Good afternoon, everyone. Sorry for the delay. Welcome to this week's HAO colloquium. Today our speaker is David Kulitz, and Dr. Kulitz received his PhD at Queen's University Belfast in 2014. And from 2014 to 2017, he worked as a postdoctoral fellow at Queen's University Belfast. And in 2017, he joined Aberystwyth University as a research fellow and a lecturer. And in 2023, he was appointed as an assistant astronomer at the National Solar Observatory. And his research interests include plasma diagnostics in the solar atmosphere, high-resolution spectroscopy, and spectropolarimetry, and also fine-scale structures of the photosphere, chromosphere, and the solar flares. Today, Dr. Kulitz will be talking about the striated solar photosphere observed at 20 kilometers resolution. So please go ahead, Dieter.
Thank you. Thank you for having me today. It is always great pleasure to give HAO colloquium. So yes, I will talk about striated solar photosphere at thickest resolution. Striation in the solar photosphere is observed in many different structures, like pores, the edges of the pores, sunspots, sunspot light bridges, and sunspot penumbra. But the finest scale striation is observed in structures called faculae, which are bright granular edges observed when active region or plages are viewed away from disk center. So here I have typical image of G-band, the faculae in G-band, taken with Tan-Solar telescope. The faculae are extremely important structures. Well, they are associated with magnetic field, we know that, and their brightness are very important. Actually, their brightness are dominant in defining solar irradiance variables. So it is very important. When I was preparing this presentation, I was a bit curious about history of observations of faculae, and I was surprised to find out that actually observations of faculae is almost as old as observations of sunspots with solar telescopes. So here I have, here I'm showing the hand drawing made by Hevelius in 1644, based on the data he took for sunspot. So we have here the sunspot that moves across the solar disk due to the solar rotation. So sunspot penumbra is resolved here, but more importantly, at the limb, this sunspot, this active region, develops some bright irregular patches comparable to the size of spots. And actually, this is faculae. So Scheiner called them faculae later, or little torches. That Scheiner was another great astronomer in 17th century. So yeah, these structures were discovered in 17th century, and now we know that the contrast of faculae is much lower compared to the sunspot. So they are much more difficult to see when they are close to the disk center. Okay, so first obvious question is why faculae are bright? And now we know that equilibrium and energy balance of the magnetic flux tube in the photosphere creates low density, low opacity environment along the flux tube, which results in a depression of optical depth unity surface. Okay, and as a result, when we look these structures, these magnetic flux tubes, at the top, what we see is bright points. But when we see with angle, we see edges of the granular walls, and they are hotter than neighboring atmosphere at the equal optical depths. So they are hotter, and that's why we see them as bright structures. Okay, so the striation in faculae was discovered with 0.1 arcsecond observations with 1 metaclass solar telescopes. So here I have image taken from Lights et al. 2004, which is one of the first observations of photospheric striation. And yeah, we can clearly see these dark stripes that are crossing the bright facular elements. So based on these observations and some other observations obtained in G-band with 1 metaclass solar telescopes, it was estimated that average width of individual strands is around 0.1, 0.2 arcseconds. And this is very close to diffraction limit of 1 metaclass solar telescopes. So this immediately raised the question, does these structures exist even smaller spatial scales? Well, this is what we have with Dikist. This is what 4 meta aperture can give us. So yeah, even without any measurements, we can see that, yeah, these structures are finer and narrower compared to what we used to see in previous observations. Let me discuss a little bit more about this Dikist observation. So we used VBI instrument, which is visible broadband imager, very high resolution, very fast imaging system at Dikist. So we used G-band and H-beta channels. I will show you later some H-beta images, but let's focus on G-band now. The spatial resolution of these observations are 0.02, 0.03, which is basically the resolution limit of Dikist at 430 nanometers. The target was large plage region at the southeast side of the sun. And the mu, the heliocentric cosine of heliocentric angle of these observations, is 0.85. Okay, and we can see how well these plage structures are resolved in this observation. So the field of view is dominated by these bright facular areas, and the zoomed G-band image shows that all elements of facular elements are very well resolved. So we can see these brightenings, facular brightenings, which are typically bordered by dark lanes. Okay, so the beauty of the facular observations is that you can immediately see from the image, you can immediately see which side is disk center and which side is limb. So those dark lanes always are towards the disk center side. So we can immediately see that. And there are striations, right? Striations everywhere. So just to enhance that fine scale details, we used simple image processing technique, in particular, the Gaussian subtraction method. But even without that extra image processing, we can clearly see those fine scale striations in the G-band image. Okay, so the widths of these structures are about 20 to 53 kilometers. So we selected randomly about 8 structures in this field of view and measured full width HAO maximum using Gaussian fit of the intensity crosscut. And yeah, as you can see, these structures are extremely narrow. And actually, many of them, the widths of many of them are close to the diffraction limit of Dicist. 20 kilometers is like resolution limit of Dicist. And well, this raises again the similar questions what we had when we start resolving these structures with man-meta telescopes. Do they exist even smaller spatial scales? Well, we cannot answer these questions at this moment. Okay, so to interpret and understand these things, we decide to reproduce them in numerical simulations. And Matthias Rempel did these simulations. So to match the Dicist resolution, we used horizontal grid space equal 7 kilometers, which gives us roughly 15-20 kilometers spatial resolution. And yeah, so the horizontal domain covers the 2.24 megameters below the photosphere, below tau equal 1 layer, and 1 megameters above tau equal 1. So the magnetic setup was selected in a way that we get very strong network fields like kilogauss with kilogauss trends, which is good approximation for plage type atmosphere. Okay, so we took one of the developed snapshot, and initially for the test, we calculated synthetic blue continuum images using RH code. Han did these calculations. So initially we saw these striations in the blue continuum images, early Dicist blue continuum images, and we kind of started analysis and then working on that. That's why we simulated this 450 nanometers intensities fast. So here you can see, we see the images for different mu angle, which varies from 1 to 0.85. And we can immediately see that, well, center to limb variation is obviously very important for what we see in the images. And then we calculated G-band synthetic intensities as well. So we did it for the disk center at mu equal 1 and at mu equal 0.85, which is mu of our observations with Dicist. Even at the disk center, we can see some striations. But for this mu, the striations getting longer, and we are getting some predominant direction. So geometry and viewing angle affects a lot, again, what we see. Okay, here I have G-band spectrum calculated from Muram and RH code. And yeah, that orange one is Atlas for comparison, and they are very close to each other. So G-band spectrum, that the spectral range is very complicated spectral range, right? We have the hundreds of molecular lines, hundreds of atomic lines, and almost all of them are reproduced perfectly. So yeah, this is really nice to see. It just shows how well we can synthesize and reproduce the photospheric physics. So to get the close match, we multiplied our synthetic data to the VBI-given filter, which is basically the transmission filter, given here as the green line. And then we integrated synthetic data along the wavelengths, covered wavelength range, covered by thickest filter. And here is the result. Okay, so we have synthetic G-band and VBI G-band. And yeah, these filtergrams looks very similar. So all ocular elements like striation, dark lanes, bright granular walls are reproduced by the synthetic in the synthetic data. Okay, then we measured obviously the widths of the structures in the synthetic images, and they are very similar to the observed ones. So the smallest scale striations have something like 17 kilometer widths, which is again the smallest scale which we can measure in this 7 kilometer grid space simulation. So again, question is same here. Does these structures exist at the finer scales? Well, actually, we are now analyzing the higher resolution Muram simulation and synthetic G-bands, and it looks like that there are shorter, narrower structures in the solar photosphere. Okay, we also calculated the height of this with Muram simulation. We also calculated height of the surface where optical depths reach unity. Okay, for different at different spectral positions along G-band. We can see that map here, the height map for this subregion. So this is very useful because it can help us to understand why we see these facular features, facular structures. Let's start with facular brightenings. So yeah, to synthesize the intensities at mu equals 0.85, we modified our Muram cube by shifting each layer with respect to the layer above with the corresponding angle. So in this way, we adjusted the slanted line of sight to the vertical. So now the vertical direction is mu equals 0.85. Okay, and so now if the line of sight passes through the magnetic flux element, magnetic flux tube, then obviously due to the reduced opacity and density, we see deeper layers, and the tau equal 1 layer falls into the granular wall, which are hotter than neighboring photosphere at the same optical depths. And that's why we see these facular brightenings. Okay, now for dark lanes, if line of sight is close to the magnetic flux tube, but does not pass through the magnetic flux tube, then tau equal 1 layer forms at the same height as the neighboring granular top, but it feels the lower temperature. Okay, so it could fall on the magnetic flux tube or little bit inside magnetic flux tube where temperature is lower. But even if it is little bit outside magnetic flux tube, the tau equal 1 layer, it still falls at the lower temperature. This lower temperature comes due to the increased radiation into the flux tube from the neighboring, from the surrounding area. Okay, and this is why we are getting dark lanes. So again, those dark lanes, if we look the full map of the tau equal 1 height, we can immediately see that the geometrical height of the tau equal 1 layer for dark lanes are at the same level as neighboring photosphere. So here the red contour marks the dark lane in G band, and yeah, as you can see, the formation height is same for this dark lane and neighboring granule. However, the temperature is lower there, and that's why we see them as dark lanes in G-band filtergrams. Okay, now how about striation? So this tau equal 1 layer map clearly shows that dark striations coincide with elevated tau equal 1 heights. So there is perfect match, right, between those fine structures seen in that tau equal 1 map and G-band filtergrams. The difference between formation heights are really small in many cases. It could be like 10 kilometers. 10 kilometers is like horizontal resolution of this simulation. But that 10 kilometers difference is still there. And question is now what creates this formation height? What creates these changes in formation height? Well, obviously it should be magnetic field. And we checked the magnetic field BZ in the Muram simulation, and we compared it to the striations. So here you can see at the bottom panel, you can see the intensities along these red and blue lines at the top from BZ and G band. And they are correlated. They are clearly correlated, which means that dark striations in G band corresponds to the lower magnetic field in BZ. So magnetic field variation produce these G-band striations. We also checked the signatures of these G-band striations in polarization profiles. So we synthesized Stokes profiles from the same Muram cube. And at the right-hand side of the slide, the right panel shows Stokes V synthesized at iron 1 630 nanometers. And again, there are perfect correlations between polarization signature and G-band intensities along the lines that are crossing the dark striations. So there is no doubt that these striations, these fine-scale striations, are produced because of the magnetic field variation. Okay, now the next question is, where this magnetic field variation is coming from, what creates this variation. So from images, we can say that these striations appear more or less regularly spaced, nearly constant distance between the stripes. Does this tell us anything? So as I mentioned already, these striations can be seen at the disk center as well. They are much shorter at the disk center, but we can clearly see them. And so here I have, again, BZ from Muram and synthetic G-band at the disk center. And we can see from these images that foot points of these striations coincides to the deformed magnetic flux tube boundaries. So yeah, we can just directly compare. The striations are sticking out from the places where magnetic boundary is corrugated or deformed. So, so what is happening, obviously, is that corrugated magnetic boundary produce some sort of inclination in magnetic flux tube, and along that inclination, the opacity, inclined magnetic flux tubes, opacity properties is changing. Formation height of tau equal 1 is changing, and that produces dark striations. Same way as we already discussed for mu equal 0.85 observations. But so now question is, what creates these boundary corrugations? One possible explanation, one possible mechanism that produces these corrugated magnetic surfaces could be interchange instability. Okay, very famous MHD instability that has been used to explain many things in the solar photosphere, like, for example, fragmentation of G-band, fragmentation of small-scale photospheric magnetic concentrations, stability of sunspots, and so on. Let me remind you what is interchange instability. So, if we have some perturbations of boundary of magnetic flux tube, and that perturbations does not change the volume of the flux tube, then we can say that the total energy, total internal energy of the magnetic flux tube is saved, unchanged, because we are just exchanging thermal and equal amount of thermal and magnetic energy. And in this case, the instability that can develop is called interchange instability. We also have more poetic name for that, the flute instability, that comes from that classical architectural column, which has this horizontal, the vertical stripes. So there are some nice theoretical works that studies how important this interchange instability could be for magnetic flux concentrations with the same size as we have in plages in the solar photosphere. And it indicates that those strong magnetic flux concentrations should be unstable against flute instability. One can easily derive that stability condition, stability criteria, which is given here with this formulae. So if the horizontal component or radial component of magnetic field decrease as a function of height, then flux tube could be stable. but if it's increased as a function of height, then flux tube can be unstable against fluid instability. So I think it is the very interesting and promising mechanism to explain those how these corrugated magnetic boundaries are produced in the photosphere. However, yeah, as far as I know, this has not been studied and proved in the observations or in the numerical in the simulated data. Okay, another important question related to this photospheric striation is their connections to the upper atmosphere. So here we have H-beta image obtained for the same field of view what we have for G-band, and you can see how complicated how complicated the atmosphere is above these facular regions. So we have lots of fine scale, very long fibrils there. And again, question is, are there any connection between photospheric striations and these fine scale magnetic structures which we have in the chromosphere and possibly in the corona as well? This is just co-aligned G-band and H-beta images taken almost simultaneously, and it clearly shows that these fibrils are rooted into these magnetic flux concentrations. Well, we know this for a long time. The spicules, fibrils, all those chromospheric structures are rooted in magnetic flux concentrations, but we are struggling to find kind of one-to-one correspondence and just identify exact position of the foot points of spicules and fibrils. Now, when we published this work, we also wrote the NSO blog and press release for general public, and in those press release we used analogy of curtain, the magnetic curtain, just to deliver in a the easy way the results to the general public. But actually, that magnetic curtain analogy is quite a good analogy. So we can consider these magnetic flux concentrations as 3D magnetic curtains, and with lots of ripples, and those ripples are changing the light transparency of the atmosphere, and we are getting these dark and bright shades. But interestingly, this analogy of magnetic curtain FaceTime was used in the paper published by Judge et al. 2011. Very interesting and important paper. So in that paper, the authors suggested that spicules, well, at least some spicules, could be the warped tangential discontinuities that producing the optical superposition, like striations in the curtain blowing in the wind or moving whatever reason. So in the follow-up paper, Judge et al. Has lots of discussions and some very strong arguments to support this hypothesis. So as we know, there are spicules and some properties of spicules, especially those fast type 2 spicules, that simply cannot be explained by traditional spicule models like flux tube and flows along the flux tube. And if we consider them as the tangential discontinuities in the magnetic curtain, some properties some observed properties does make sense and can be explained easily. Of course, this idea is still hypothesis, and it needs to be proved or disproved. But at least at the photospheric level, we saw that those small-scale photospheric striations are produced. It can be understanding as the magnetic curtain. But again, question is, are they connected to spicules or fine structures, other fine structures in the chromosphere? This is just the direct quote from Judge et al. 2011. So they are arguing that magnetic structures arising naturally from the fluid sheet configurations, which is observed in the photosphere, can develop as tangential discontinuities in the upper layers. So I think this is very interesting, and we just need to have right data. Well, obviously, we need to do precise chromospheric polarimetry to check this idea and to investigate if there are connections between photospheric striations and magnetic structures in the upper atmosphere. So yeah, I think DKIST has potential to provide such data, and I really hope we will get this type of data soon. Yeah, okay, so yeah, this paper, the Judge et al. Also has discussion about so if we have these perturbations or distortions at the photospheric level, these magnetic distortions, they should propagate in the upper atmosphere. They should have in the upper atmosphere larger amplitudes, okay? Because of the stratification of magnetic and density stratification. Which means that, yes, they should influence at least what is happening in the chromosphere and corona. Okay, here is my conclusions. So we know for a long time that G-band images are very good proxy for magnetometry. Right, we know that G-band bright points, even in the quiet sun, corresponds exactly, the sizes, for example, corresponds exactly the polarization signatures, the magnetic structures which are seen in magnetograms. But there is more than that. So with this work, I think we can confidently say that all those small-scale striations are also proxy to some magnetic field variations and Wilson depressions like up to 10-kilometer scale. So, well, yeah, origin of the magnetic field variation still needs to be investigated. And the dynamic, I have not mentioned about dynamical nature of these things, but we can predict, and well, we can actually see in the observations and simulations that they have very short dynamical time scales, which is not surprising because they have short spatial scales, and the variation of parameters like magnetic field, Wilson depressions are extremely small, so they should have short dynamical timescales, and these dynamical timescales could give us some important information about some fundamental processes in the photosphere and possibly in the chromosphere and corona. Okay, I would like to finish with this slide. So I think it just demonstrates how difficult solar physics is. Something that was discovered in 1644 is still the subject of research of modern solar physics. But it also shows how far we went. I mean, the resolution of this Hevelius data is estimated as 10 to 15 arc second, and going from 15 arc second to, well, potentially 0.02 arc second is quite a journey. Yeah, I found this really exciting. So thank you very much for your attention, and if you have questions or comments, you are more than welcome.
Thank you for this very interesting talk, Dato. And do we have any questions from the audience?
I'm not very well versed on the current capabilities of the DCAST instruments, but what is the prospect of getting magnetic measurements of these to corroborate the MURAM simulations?
So I really believe that we can get such magnetic field measurements with DCAST. So we have, at this moment, we have, well, two polarimeters like DL, NIRSP, and WISP. But problem with those two instruments is that because of their nature, they cannot deliver diffraction limit resolution observations. But, well, we are installing, well, it is already installing, and it is under testing regime, the Fabry-Perot interferometer, VTF, which will deliver the diffraction limit resolution observations. And I really hope, and I believe that that instrument will be able to provide some very good chromospheric polarimetric observations that will allow us to resolve actually these things in magnetograms, chromospheric magnetograms, and, well, photospheric magnetograms as well.
I have a question. Are there any spectroscopic only observations of this striation and how they vary over time?
Yes, there is one paper published by Bart de Pontiu, I think 2007, and they studied the dynamic of these striations, and they found some interesting things, like there are some swaying motions, some fast appearance, disappearance of these structures, but again, that was done with much lower resolution, and we now know that you need really high resolution to do this.
I was wondering more if the variation in the striation is also related to line of sight variation of the emission line or stuff like that.
Yeah. I mean, line of sight effects are extremely important for them. So if something is changing in front of them, they feel that. But yeah, you need really fast cadence, like very high time resolution to study this. For these observations, the time resolution is something like half a minute, and that was not enough to study properly. So, but we hope that we will get better data, and then we'll study these temporal evolutions of these structures.
Looking forward to hearing more about it.
Yeah.
A question. You mentioned this fluid instability, and I don't know anything about it, but I thought I heard you say that it only appears when there's a vertical gradient in the magnetic field that of a specific sign. I can't remember whether it's decreasing or increasing.
Yeah. So the px, the radial component should increase as a function of height. I
Okay.
think this is the basic stability criteria.
For that to form, or yeah.
Yeah, for the magnetic flux tube. And yeah, there are some works in this paper. This is very nice paper, and this paper estimates that very close to log tau equal the tau equal 1. This criteria is fully so that those plage type magnetic flux concentrations should be unstable against fluid instability. So
I guess my question is then, is that condition satisfied in the simulations? Have you looked at it?
oh yeah,
Here?
yes. So I'm kind of doing it now. Yeah. So it is quite challenging. There are some challenges. It's not straightforward. You go and yeah. But yeah, we are doing this now. Yeah.
Thanks.
Do we have questions from online people?
I have another question. Are you gonna also look at, you said that the interval between them is pretty constant over time. Are you looking into them being something like wave propagation, wavefronts around the edge of the?
Yes. So yeah, this is a very good question. I mean, in MHD wave theories, there is actually MHD modes called fluting modes, which I believe is related to that fluid instability. So, yeah, this could be related to some sort of wave motions in the photosphere. Actually, the Pontiu paper has some findings that indicate that wave could play the important role. So yeah, it could be important. Yeah, the waves there.
I have a question. So you mentioned the possible connection between the photospheric striation and the structures like the specules in the chromosphere. Can you see that in the Muram simulation?
Oh, okay. So in Muram, we cannot simulate the chromosphere in this. Yeah, so this Muram cube only covers the photosphere. But yeah, this could be the possible way to the way forward. I mean, I guess one could somehow simulate chromosphere with Muram snapshots, at least in LTE, or yeah, I don't know, but yeah, one can investigate this. But again, the problem is that we cannot really properly simulate the chromosphere and its fine structuring. In the photosphere, mostly we understand photospheric physics very well. We can do things, but in the chromosphere, it's much more challenging. So this is why I have more hope in the observations. If we get good chromospheric observations, including polarimetry, you can really find some connections between this phenomenon. Yeah.
Yeah, Phil, go ahead.
Thanks, David. I think you're really onto a good approach here, which is to focus on the observations. And what I'm struck by, in seeing as you have this figure up, could you zoom it out again so we can see more of the figure?
Which one, the observations or the data?
The observations here, yeah, the one you had right there. So include the one with the H beta,
Oh, okay.
the one you had.
Yep.
So what I see here is this is plage, which is mostly unipolar. And
Yes.
a couple of things strike me here. One is that you ought to be able, with H beta, to connect. Both have signatures in the upper chromosphere and in the photosphere, and you can see it in this figure. You can see the bright plage underneath and then the darker stuff. You know, irrespective of how they form, you should be able to trace those thin black things down as where their roots are and see where they're coming from. And so I would say H beta is a very, very nice thing because you're looking at deep down and high up at the same time with a relatively broadband instrument. So it should be possible to make a statement here. Of course, you might end up making a statement about the formation of the line more than the magnetic conductivity. But I really like your approach of going to the absolute highest resolution you can. And I think there's some exciting conclusions that you'll be able to draw, you know, with DKIST here. And I think this is a perfect DKIST target to address chromospheric structure and dynamics for the first time. So congratulations on a wonderful, wonderful piece of work.
Yeah, thank you, Bill. Yeah, this is interesting. Yes. So yes, I also like very much the H beta. You know, the way the filter works there is that we can get the photospheric features, even granulation, you know, and we can get the fibrils. But one problem here is that these images are not quite simultaneous. So the way the VBI instrument works is that you are taking these images sequentially, and this was like in mosaic mode. So difference between these images are something like half minute. So yeah, it is challenging, but I mean, yeah, one could try this. Yeah, if we can find that direct, if we can trace those fibrils directly to the photospheric elements. Yeah.
Yeah, it's been a big missing part of the puzzle for a very long time. And but H beta is a nice part of the spectrum, not too opaque, not too thin. And so, yeah, the other thing is that I look at this and I have to remind people that plage is very strong in the solar transition region. And the reason I bring that up is that there are essentially no loops, small cool loops here. And I've been saying this for 15 or 20 years, but people still think that the transition region is formed out of these cool loops. But for that, you must see the loops somewhere connecting between opposite polarities. And there's just no room for the opposite polarity flux to create a transition region. So that is a refutation of the cool loop model of you know, from the 80s, people like Dowdy, people like you know, and it's just, I don't know why people persist with a model that's manifestly magnetically not possible. You can't fit cool loops into the observations over plage, and there's no room for the opposite magnetic fields. So the transition region has to be formed in unipolar regions. That's simple as that. But thank you.
Do we have any more questions? If not, let's thank our speaker again. And yeah, we'll see you next. See.